Okie doke. So today, since so many scans that we do are 3D scans, I want to sort of go over this in a little bit more detail, because there's a few counterintuitive properties of 3D scans, and I'll talk a little bit about sort of motion and what do the pulse sequences look like, and motion, and how big your volume is, and how it's sort of represented on the scanner. But before I do that, I'll just go back over what we did very quickly in 2D. And so what I was arguing is that when we looked at frequency encoding, we said you normally do this with a gradient on, but it turns out that's actually equivalent to, so you turn the gradient on and then record data points with the gradient on. But it turns out that's actually exactly equivalent to turning the gradient on for a little bit and then recording with the gradient off, and then turning it on again, recording with the gradient off, like that. So that thing is actually equal to that. So if you think about phase encoding, so normally the definition of phase encoding is that you do it before you record. So the idea is you pick out a particular phase encoding step, whatever, one of these ones, and you do that, and then at a later point in time you record. And so that sort of seems distinct, because this one, you're changing the frequency during the recording. This one, you're not changing the frequency during the recording. But it turns out, since frequency encoding can also be thought of like this, where you turn the gradient on and then you turn it off and then you do a recording, it's pretty much the same thing. So you can see that it's the same thing. You turn the gradient on, it does something to the spins. You turn it off, and then you do some recording. And so then, when you look at it this way, you can see that basically frequency encoding and phase encoding is the same thing. And there's no requirement. Don't get into the garden path. There's no requirement that you have to have multiple frequencies on, because when you have the gradient on, there's multiple frequencies, because at the high end of the gradient they're processing faster. There's no requirement that you have to have multiple frequencies on in order to get frequency encoding. So it's really just something you did to the spins that sticks. You messed with the phase of the spins when the gradient was on, and then it stuck. It just persisted, and then you can just record it with all the spins at the same precession frequency. So that's the fundamental insight on why it's exactly the same. It's basically the same thing, as frequency and phase is the same thing. And we'll talk about that when we talk about the second part here, of how to sort of back off from the complicated stripes and just graphically get a feel for what gradients do. They just kind of move you around in K-space. So to start off, what I wanted to do is just talk about a 3D scan. And so what is a 3D scan? A 3D scan is, phase number 2. So you basically just add a second phase encoding direction. And like I said, like when this first happened, when I first saw this, I said, it doesn't compute. Like, I thought you have to do either frequency or phase, and then how can you do a second phase? But it turns out frequency is also a phase. So there's just 3 phase encoding things going on. And so what does that actually look like? A very simple pulse sequence. And I'll just draw out a simple without all the details, but the 3D gradient echo. So this is the most common kind of structural scan, like a T1 weighted scan, or an MP rage is an example of something like this. And so the way it works is, so we have we've got here's the RF, and so the RF is typically, especially with a 3D sequence, the RF might be a very low flip angle so that we don't lose longitudinal magnetization. So we'll call that sort of an alpha pulse, just meaning like it's not 90, it's some small flip angle. And then here's our gradients. So here's the Z gradient and the Y gradient, the X gradient, and then here's the signal that comes out, and then here's what we record. So this is Y, X, sig, and record, because we don't record the whole signal. So what's the first thing that's kind of slightly weird about this? And the first thing is we don't turn on any slice select gradient, because we just want to excite the whole head. Now that's not always true. We might want to turn on a very thick slice that selects the whole head. So there's two different ways you could do it. You could just say, well, I'll just zap the whole thing, shoulders, everything, and just, you know, not worry about it. Or you could say, I'll stimulate a slice that's so thick that it selects the entire head, and you can just select that on the scanner. You can. There's various reasons why you might want to do that. One of the reasons is if the slices are going this way, you might get some wraparound for reasons we'll describe later, and so like some part of your body would sort of wrap around into your brain. Whereas if you've got the scan set up sideways, or you've got air on either side, the wraparound problem isn't there. So there's several reasons why you might want to do a slab selective. So they would call that, so either nothing, or slab selective. It just means thick slice. So that's the first thing. But let's just assume we didn't do any slabs, any slice select at all, and so we just did the whole head. So then what you do is you've got your phase encode. So after that pulse turns off, we do all the different possible phase encode steps. So there could be 200, 256 of these guys. Just pick one of those. And while we're doing that, we also do, we wrap up the spins for the readout all the way up to like 128 stripes. And then we do a readout. But then how do you do another phase encode? Simple. You just turn on the Z gradient. So just turn on the slice select gradient. Now, when you look at this diagram, since this means, for each of these, and then we've also got for each of these, if there's 256 settings here and 256 settings here, that means we've got to do, 65,000 combinations of these, and then do a readout for each of those. So we need 65,000 readouts, and that's what happens in a 3D scan. You'll have 50,000 RF pulses, and you'll collect one line of data, say that might be 256 long. So you'll end up with 256 times 256 times 256 data points. So if we look down here, so we're going to get, a big FID here that we'll ignore, and then here's our echo that we're actually recording. So the only thing we record is just here's all our recording data points here, like 256 recording data points. So that's pretty much it. So it's remarkably simple. The only part that we haven't discussed is what about when you want to do another pulse? If you're going to collect 65,000 RF pulses, you're going to have to do it pretty quick, otherwise the person's going to be in there for overnight. And so you've got to do, so the next RF, so typically you do things like, let's put on a big gradient here to get rid of any transverse magnetization that we have. And we also might do something like the next RF pulse, set the phase, you know, to some special angle that will have the effect of disabling any of the leftover transverse magnetization. So there's some additional things before you do it again, but the idea is we need to do it again really quickly. And how quickly? This time right here could be something like 7 milliseconds. So that's really quick. That's just, you know, less than a hundredth of a second. So that means that you're recording 100 lines of data per second. And that's why the scanner sort of sounds like that sound was 100 of these gradients going up and down. So it comes out like an actual pitch because you're recording so fast. So, you know, every you have another RF pulse every 7 milliseconds. So that's what a typical 3D scan looks like, and it's kind of deceptively simple. All you did was you just basically turned on another set of gradients. Now, if you wanted a slab select in there, then you could stick another slab select with a little slab select fixer in there, you know, before you did the second phase encode. And so if you ever read any of the literature, so this is an important point. So this is the readout direction. So that really gives you a cue as to frequency encoding versus phase encoding. It's not frequency encoding versus phase encoding, it's direction. So readout directions means what's the direction in space that the readout gradient is being applied. And so this is the phase encode direction. And that's an actual physical direction in space. It's the y, is the y-axis. And so what is this one called? So unfortunately, this one sometimes is called the second phase encode direction, but more commonly it's called the partition direction. So it will say this sometimes on the scanner interfaces, or if you read any of the literature, you know. So this is called the partition direction, and the reason for that is that the partition is one setting of the second phase encode direction for all the settings of the first phase encode direction. That's kind of like a partition, a chunk of, so it's a chunk of data that corresponds to, you know, one setting of this guy, and it includes all the different settings of the line that was recorded for each of the different settings of this one. So that's the derivation of the term partition. When you hear it, when I heard it the first time, partition, what the heck does that mean? So it really just means the second phase encode direction. So that's the basic 3D. So what's actually going on in real space? Like I said, what's going on is now you've got a cube of data. So instead of sort of stamping stripes onto just a slice, you're kind of stamping some arbitrary collection of stripes onto this whole cube. It goes through the entire cube. And so it'll have some arbitrary spacing. You've got to do all the different spacings, and then some. So, you know, another one. So that corresponds to This corresponds to just one point here. Just a single point there. So another point, so since this gradient, the readout gradient is on, these stripes are going to be rotating around the readout direction. So, at a later point, and depending on what the readout direction was, if the readout direction was, say this direction, they're going to be rotating around that. So, a little later point in time, the stripes will have rotated this way. But, it's going to be sort of a complicated rotation in 3D. So this is at some later point in time, because the readout gradient was on, and so it continued to rotate these guys. And so, what is the situation before you turn the readout gradient on? Well, we're sort of like doing this wrap up to 128 cycles in the readout direction at the same time as this. But if we move this guy over and just looked at what happened when we turned on these two, those would just cause stripes just in the Z and the Y direction and not the readout direction. And then when you turned on the readout, it would start rotating them in a third direction. So, but physically what's going on is you're basically just putting, you just have to record every possible combination of spacing of those spin phase stripes, and then every possible combination of rotation of those stripes. So there'll be a total of like 10 or 16 million data points, 10 or 16 million different combinations of orientation of the stripes and then spacing of the stripes, because they have to go from like one stripe across the whole volume up to 128 stripes across the whole volume. So why do you want to do this? Well, you get much better signal to noise for the simple reason that you're activating the whole volume at the same time. So if you do a slice select, what happens is you just pick out a little chunk of tissue like that, and you get some, and then you put stripes on it, and you got to put all the different stripes on it, and then your head coil picks it up, but you only got data from a small chunk of the brain. In this case, we're hitting the entire brain every single time, so we get a lot more signal because every single data point contains information about the entire brain. So when you see this, so this this is real space here, real physical space. Not K space. That's actual sort of real XYZ space. So what's X, Y, Z. So it's actual real space, and so every single data point that you record contains information about the entire brain. And so that's a much more efficient way of collecting the data, and that's, when this came around, started getting really practical in the 90s, suddenly you could collect much thinner slices. So there's several difficulties with collecting thin slices with the slice-based select. And one of the problems is it's very hard to make a very thin slice this way. And the reason is because how do you make a thin slice? So a thin slice requires steep gradient. So you could run the gradient up to the maximum steepness. There's a certain maximum level of the gradient, and then the amplifier can't do any more. So a steep gradient, but then you also need a narrow bandwidth RF pulse. Now, if you remember the Fourier, what does that mean? That means long in time. So in order to make a thin slice, you need a narrower band of frequencies. A narrower band of frequencies corresponds to a wider, a longer sync pulse or Gaussian pulse, whatever. So then that starts cutting in. So that means that this thing is going to get wider, and if that thing gets wider, then it will use up time. And so there's a pretty clear limit. You can't really go much below typically about 1 millimeter slices. And the other thing is that even then you're making compromises. The slice profile isn't very good, and so you tend to start getting bleeding into the other slices. And so basically it wasn't practical to make a 1 by 1 by 1 scan, and also it takes a lot longer. To do a 1 by 1 by 1 scan would take like an hour if you did it by slices. And so this completely revolutionized collecting 3D data by doing this second phase encode direction. So it has a couple slightly strange. The last thing I wanted to mention was, well, yeah, I was going to talk a little bit about motion. So one of the problems you can see here is, what about motion? Well, now you're kind of in trouble, because the problem is, since every single data point comes from the entire head, if you move, it's going to mess up your data big time, because what does it mean when you move? Well, you've got a brain in there. So here's here's the brain sitting in there. So you got the brain in that volume. If you move that brain, if I move that brain, that's not good, because what that means is that the data is going to, the stripes are going to go to the same place in space, because the position of the stripes is due to the settings of the gradient. So if you move the brain, what happens is it will stamp the slices onto the wrong part of the brain. Then when you do the Fourier reconstruction, the inverse Fourier transform is the same as the forward Fourier transform. It's just basically a sum. It's basically a sum of stripes. And so you sum up all the data from those stripe patterns, but they're off, they're off from each other. And so what happens, you'll get a picture of the brain like this, but it'll have all these little sort of circular, typically these like circular little striations in it like that. And then the sulci will sort of looks like somebody sort of, literally just looks like somebody moved them. And so they'll sort of be blurred out. So that's one of the problems with this kind of scan. There's no easy way to fix the motion artifact in it. So because you'd have to somehow fix it in the Fourier domain. People have tried to do math to actually try to fix it directly, but it's extremely difficult. So you can't just take the image and somehow get rid of the motion. So that's one of the reasons why there's been a lot of effort put into trying to do a navigator scan to try to correct the motion and follow the brain, or like we have use this camera system that tracks a marker. And so then when the person moves their head, what will happen is that will feed back into the scanner, and it will rotate the stripes so that the stripes end up on the same place on the brain. That's how the prospective motion correction works. You could also do a different setup where you do a quick and dirty scan to figure out where the brain went to, and then use that information to rotate the gradients, change the gradient amplitude so that the stripes rotate, so to cancel out the motion. So that's one of the problems with 3D imaging is that it's more susceptible to motion artifact, because basically you're collecting 5 minutes of data, and every single data point, all those 10 million data points, came from the entire head, and so any motion across that time is going to mess it up. Whereas if you just collect a bad slice, whatever, you can just you can actually try to fix that later, like you would for for a typical functional MRI scan. So there's no way to do the motion correction the way you do it with a functional MRI scan where you try to line it up. Okay, so that's motion, and then motion artifact. And then one last thing that's very weird about, which relates to the idea that all the data comes from the entire brain, is that so one of the things is on the scanner. This sometimes is called slices. So it's not slices. So you ask. When you ask, on the scanner, you can say, how many sagittal slices do I want in my MP range? And you could put in 176 sagittal slices. But they're actually not slices because there's no slice select. What they're partitions, or partition steps. So sometimes that field will say 176 partitions. But on our scanner it says slices, but it's actually not slices. And it gives rise to some counterintuitive things. So here's, happy person in the scanner. So if we select, say, 176 sagittal slices, because we want to sort of save time. So if we select, if this is 176, say, then that, a lot of times I'll see people sort of carefully sort of reducing the number of slices so that they're just as big as the head. You'll get an image out of that. But what if you do just more slices of air? So this is air here. So what if instead of say 176 I do say 256 slices? Most people would think, wow, why do that? You're just wasting time scanning air because, but you're not. Because every single excitation pulse, all you did was increase the number of phase encode steps in the z direction. That just means you have more data. So with a 3D scan, if you increase the number of partitions out into the air, your image gets better. And the reason it gets better is because you collected more data. And it gets better because each data point comes from the entire head. So it's not really a slice. So that's pretty counterintuitive that you can get better data by recording quote unquote slices of air. But you can understand this if you realize that in a 3D scan every data point comes from the entire head. Okay, so let's talk about now, sort of back off to a slightly more abstract picture of sort of what do gradients do. Well, it's not just gradients. What does RF and gradients do in K-space? And basically, the way people think about this is, again, it's always just abstracting down to some simple physical model. It's a simple physical model of, K-space is a two-dimensional or three-dimensional physical space. And what do the gradients do? They just move you around in it. And so that's the way to think about what applying a gradient and changing the stripe pattern means. The way to think about it is it just moves you to some other part of K-space. So if we start off, so K-space position is set by integral integral of one of the gradients over time up to record point. So just to say that with an equation, so the k space position, which means spatial frequency, so like how, or literally how many stripes. So how many stripes is equal to that's the gyromagnetic ratio, but that's just a constant, so we don't have to worry about that. So it's basically the sum from time equals 0 up to the current time. So this is record time. I'll give some examples of this. So from 0 times 0 up to record time, we didn't say what time 0 was yet, but we will. So it's the integral, or area under the curve, of whatever the gradient was at a particular time, because the gradient can go up and down, summed across all time. So that means the area under the curve of the gradient. That's what this, so it's right on. So this is area under curve, under gradient curve. That's all that means. So what about time 0? There's the other we should add something here. So the RF pulse, assuming there was no transverse magnetization laying around, the RF pulse basically means go to K-space center. Forgot to put that in there. So when you do an RF pulse, you go to K-space center. What's the K-space center? All the spatial frequency equals 0. So what does that mean? So that means K equals 0. So that sets you, that basically lines up all the spins. When the spins are all lined up, you're in spatial frequency 0. And then you turn a gradient on, and then it just depends on how strong the gradient was on, and then how long it was on. So this is like the general, this is the general equation. So this could deal with a situation, where you do an RF pulse here, and then you just turn the gradient on in some bizarre pattern like that, and then turn it off, and then record a data point there. And then what that would do is, it would say, okay, this equation would say, figure out that area, and subtract that area off, and then figure out this area, add them all up, and whatever you get, that tells you where you are in K-space. So this is, so this equation would work in this general case. But, most of the time we're thinking of a much simpler case, like, something like this. We just turn the gradient on like a square. And so if we turn the gradient on like a square, all we need to do is just find this area. And so what is that? So this equation sort of, with a simple setting like that is just equal to, this equation just turns into, K equals, gradient times time. You can sort of see it here, because here's the little sort of tiny bit of time that we're summing across. So this equation will just boil, this integral will just boil down to, you can see what the difference, here's t, and then what's the area under the curve, and this is basically just g. So just g times t, it's just the area of that gradient, corresponds to the place you get to in K-space. So what that implies is if you have like a, so say you have something like this. So you leave the gradient, so 0, 1, 2. So you leave the gradient on for for that amount of time, okay? So that will basically, and then you record a data point here. So that will pretty much equal, the following. So if instead you do, 1, 2, so 0, 1, 2, 3. If you do something like the same height, but just come up like that, and then go down like that, that area is going to be the same because these two triangles here will add up into the same thing. And you could also, so that equals that, because it's just the total area under the curve that matters, and that equals, like 0, 1, 2, 3, 4. So we could have, at 2, if we made that guy the same height and made something like that, that would add up to the same area, because you take those two triangles, add them up, you end up with this. That would be like sort of dividing it that way. So all those things are equal, and assuming you record the data here. So that's just a simple worked out example. It's really just the area under the gradient curve, and what is that determined by? That's just determined by like how strong the gradient is and then how long you left it on. And those two, you can trade those two off. So so that's a pretty straightforward way of thinking. So if you just turn the gradient on for twice as long, that's equivalent to turning gradient on for like, unit 1 is for 1 second is the same as turning it on for, 2 units, but for half a second. So now what we can think of is, let's just think about where we are in K-space. And so the very first thing is the RF pulse. And so the RF pulse will put you to the center of K-space. So if we just do a simple 2D K-space, the RF pulse will put you to the center of K-space, and this is assuming you don't have any magnetization there. If there's magnetization there, then RF pulse is not going to put you to the center of K-space. So we'll come back to that. But if you have the first situation, so RF pulse with no MT. So, and just for safety, we'll have no longitudinal magnetization. So basically, you've let everything decay. So if you let everything decay, then an RF pulse, the effect of the RF pulse is to just put you in the center of K-space. So if here's K-space, so this is KY, KX, that just goes to the center. So that's the first picture. Now, what about frequency encode? What does that do? So that, if we just turn on a frequency encode, so how am I drawing it out? Let me just do this again to have a right-left picture. So RF pulse magnetization vector equals 0. So if that's what we do, what does that imply? That implies go to the center of K-space. So frequency encode. So if we do frequency encode, and this corresponds to just turning the gradient on like that, and then recording all our data samples. what does that correspond to over here? That corresponds to, we're at the center of K-space, and we just move to the right. So up is to the right, and left is a negative one. So, but we went, we turned on the GX gradient in a positive direction, so that made us go to the right. And then here's our, we recorded our data points here. Now, what about if we do something that's more like what we typically do, which is we first go to the most negative part of X K-space. So this was the RF pulse. Here's frequency encode. What about go up here. So what about freak encode with pre-winder? So that's sometimes they call it. That's what the physicists call it. So you're winding up. You think of it as winding up the spin phase. That's why it's called the pre-winder. So if you do that, that looks like you turn the X gradient on by first going negative and then going positive for two equivalent amounts. So that this area equals this area. So what does that look like in K-space? So in that case, we go to the center, and then we immediately go to the far end of K-space. That's this part here. And so at this point, we're at the far left end of K-space. So this is Ky and Kx. And then we turn around and go all the way across K-space that way. And then record all our data points. So we don't record, so now we're recording both negative and positive frequencies, and when we come through the middle, that's when the big echo happens. So so what about a spin echo? So a spin echo, so I'll do a spin echo. So a spin echo is a little funky because what happens is we often turn on the gradient in a positive direction. And then we do our, so here's our 90. Then here's our 180. So here's our 90, and here's our 180. And then if we look at that time, so if you look at this time here, that's time tau, afterwards, so here's tau, and tau there, then we get an echo. So the echo is going to appear about here. And so now what we do is we turn the gradient on in the same direction. Let me just make it a little shorter so it's about the same as the other one. So now we turn the gradient on in the same direction. So what does that look like in K-space? And why did we go up? So it turns out that if the RF pulse is not, if the magnetization vector isn't 0, the rule is, RF pulse with MZ unequal to 0 goes to conjugate point. I can't spell. So we'll kind of flip you to the conjugate point of a 180 will flip you, sorry, 180 degree RF pulse with magnetization not equal to 0 will flip you to the conjugate part of K-space. So if we look at this picture, what's going on, we're sort of flipping back and forth madly. So first we turn on the gradient in a positive direction. What does that do? So that moves us to this part of K-space. So that's, so here's point, we'll say point A, point B. So here's point A, there's point B. Then we do a 180. And so the 180, so here's the 180, and there's point C after the 180. So what does the 180 do? It flips us to the conjugate point, and that means that we go over. So this was, that dotted one was from the RF. So what does the conjugate point mean? Well, if we had, say we'd gone down to here, it would mean that the conjugate point would have flipped us over to here. So the conjugate point, remember, is the, it's that conjugate symmetry that we were talking about, where we sort of do, you know, like to the mirror image part of K-space, but sort of flipping up and down. So that's what the RF pulse will do. So now we're pretty much where we would have been if we had done this guy. And then we do the readout again, and so the readout will then just run us back across. Now this will go back across, and so this is, you know, point C, and then this is point D. So B is up here. So that's pretty much the same as before. Now, if you do this, you could wait to do this after the 180. In that case, you'd have to make it negative. So it would be, so it's equivalent to do it sort of positive before the 180 or negative after the 180. But when you're thinking about this, like I said, it's easier to think about it in this K-space picture, and then you have kind of a straightforward mapping between the gradients, the 180 RF pulses, and the so this is the way when you're thinking about how a pulse sequence works, you think of it with this simple graphical thing, which is, you know, an RF at the beginning puts you in the middle, and the gradients just move you around. You can go anywhere with the gradients. So if you put them on at the same time, that's the last picture. So this was the spin echo. So what if we put on, you know, two gradients at the same time? So like a phase encode case, phase encode plus pre-winder. That's a very common thing we might do. What does that correspond to? So this would be, you know, we do our RF pulse, and then we put the phase encode on. Say we put a positive phase encode on, and then we also do a pre-winder, and then we do our readout, like that. So this is, you know, phase and freak. So what's going on in K-space? So now what happens is we got two gradients on at the same time. So one of them is positive, and one of them is negative. So the positive one is going to move us, you know, upward like that. But the negative one is going to move us to the left. So this is, you know, this is the KY direction, and here's the KX direction. So when we put these both on at the same time, it will just sort of move us along a diagonal direction, you know, depending on how big they are. If this was a really big one, it would move us, you know, further up. If this was like a small one, it would move us closer this way. And then when we do this one, what it just, you know, we start there and then go across. And so, and we would get, you know, a little bit of an echo as we went through the middle here, not anywhere near as big as if we were down at the center of K-space. So this is, point A here, point, B here, point C. So it's, A, B, C. And in this case, we would be, collecting a line of K-space that would all have the same KY spatial frequency, but it would have varying amounts of KX spatial frequency. So there's that. And then in the last 10 seconds, what about if we turn on 2 gradients at the same time and record data? That's possible. So one thing we can do is we could do something like, what if we do an RF pulse and then turn both gradients on at the same time? One thing you could do is you could you could go around circles in K-space like that. And you could record data during that. You could just be recording data points this whole time as you're going around. So that would be what you would call a spiral scan, where there is no clear distinction between frequency encoding and phase encoding. You just turn them both on, just like here. But instead of this case where you didn't record any data, so don't record. You're not recording here. But there's no reason. You could record if you wanted to. So you can do a spiral scan, or you can do other different kinds of weird scans. You can go sort of back and forth in this direction if you want. So this is a good way of thinking about it, not having to think about all the spin stripes. You just have a 2-dimensional or 3-dimensional K-space, and the gradients just move you around in it, and on a 180 will flip you to the opposite side. So that's the way from now on we'll be sort of thinking about how pulse sequences work in this more abstract space, but you'll get used to it. Okay, David, I think I just made it. Okay. Okay, well, I think I'm good. I'm good to end the recording. We can ask for some questions.